Hi friends, welcome back to another session on operating systems. Now we are into the second module, process management. In this we are currently looking at multi-threading systems. So in this, now let us see how many different models of multi-threading system. So what is multi-threading and what models are? So the models define how user level threads are mapped to the kernel level threads. That means how many user level threads are there, how many kernel level threads are there, how they are mapped. That is the model of a multi-threading system. Here each kernel thread will be allocated to one core of the CPU. So how does it map? So there are n user level threads and they will be mapped to k kernel level threads. So this n and k are variables, and in all there can be three possibilities, and they are many user threads to one kernel thread, or many user threads to many kernel threads, or one user thread to one kernel thread. So that's many to one, many to many, and one to one models. Let's see what each one is all about. So begin with many to one. Here there are multiple user threads and they are mapped to one kernel thread, and this one kernel thread is allocated one core of the CPU, and the thread management is done in the user space using a thread library, because these multiple threads are there at the user level. Therefore all this thread management, which of the user thread is to be connected to the available kernel thread and all that, all this management is done at the user level only, and for that we make use of thread library. And because there is one kernel thread and that one kernel thread is connected to one core of the CPU, then only one thread of the user can run at any given time, even if we have a multi-core CPU with us, because the other side we have only one kernel thread, and that one kernel thread can occupy only one core of the CPU. Even if there are multi-core CPU is there with us, it is not possible to make more than one user thread to work at any given time because of only one kernel thread. And by mistake the one user thread is currently connected to the kernel thread, and that user thread is blocked maybe for some IO operations or some other thing. Then till that is completed, no user threads can be changed. So scheduling of the user threads cannot take place, because one user thread has gone into the kernel space and the kernel is working with that thread, and if it is blocked because of some IO operations or something, then till that is completed, no other thread will get a chance to use that kernel thread, and hence all the threads will be blocked. So the positive side of many to one type of connection is fast thread creation and fast switching is possible, and because there is only one kernel is only one kernel thread is being used, so minimum overhead at the kernel level we have, but nothing comes free. So there is a negative side also. The other side of the coin, cannot have parallel execution because only one kernel core is there, only one kernel thread is there which can use only one core of the CPU, hence no chance of parallel computing. And if that thread fails, then all the threads get blocked. So that is the problem with many to one. The other option is many to many. That means we have many user threads, and there are many kernel threads. So there are many user threads, they are mapped to many kernel threads, and the operating system can dynamically manage this mapping, which user thread should be mapped to which of the kernel threads, and all that is dynamically managed by the operating system. And this will allow better scalability and parallelism, because there are multiple kernel threads are there, and each kernel thread can work with one core of the CPU, and because of that we can make sure that parallel execution of these threads can be taken up. And if these threads are independent, they don't depend on one another, whether it is about the data or any other thing, then they can be run in parallel, so better scalability can be achieved. So the positive part of this is it is very flexible and it's scalable, and we can expect a very efficient resource utilization. The negative part of it is too complex to implement, because there are many this side, many this side, and then the operating system is running around to manage the connections between the user thread and the kernel thread, and see which user thread needs next one and which kernel thread is available next time. And that too complicated scheduling is to be done. So one scheduling for the user, other scheduling for the kernel, and then mapping. It's too complex to implement, and because of this complexity, lot of overhead is created while managing these mappings. So that is the problem with many to many. Now coming to the other one, which is one to one, that means each user process will be mapped to one kernel process. Each user thread is mapped to one kernel thread, and there is a true concurrency on the multi-core system. There is no scheduling is required either in the user space or in the kernel space, because there is one user thread attached to one kernel thread, and each one is independently working, and hence true concurrency we can expect in this type of system. And this definitely allows parallel execution, and blocking is the isolation is guaranteed. That means if one of the threads gets blocked, then others just continue without getting affected, because each thread is having its own kernel, each kernel is having its own core. Therefore, if one thread gets blocked, others without any hindrance continue without any difficulty. So the positive side, high performance on multi-core CPUs, and better thread isolations are possible here, because each thread is independently working with its own kernel thread, and each kernel thread has its own core, so it is independently working. Then the negative side of that is more overhead, due to more kernel threads are there, and limited number of threads are possible, because the systems has a limitation of how many kernel threads can be created and all that. So the summary says that parallelism possible with one to one, parallelism is possible with many to many, but it is not possible with many to one. Blocking impact is very high in many to one, but it is very low in one to one. Overhead is minimum in many to one, but high in one to one. So the examples for using this on the operating system, the early Java, old version of Java was using many to one. Linux and Windows are working on one to one, and Solaris and True 64 working on many to many. So that's all about the multi-threading model. So if you find this anything interesting, so please don't forget to like, share, comment, and please do subscribe to the channel. Thank you.